Okay, and I see the admit button at the top also. Okay, now what I'm actually sharing is I'm sharing my application. You see how that, if it'll let me do that. And it'll go directly into the PowerPoint. Okay.
Yeah.
So we're recording?
Yes.
Okay. Hello, this is part 2 of Historic Watermills of North America. And for this part, we begin with how a watermill operated. This slide is a simple diagram that shows the 3 most common and popular designs for vertical water wheels. At the top, you see the overshot water wheel, which was and still today is very popular in the Appalachian region. At the bottom, you see the undershot wheel, which from what I read in a number of references is worldwide still the most popular design for a water wheel. And then in the middle, you see something called a breast shot wheel, which is kind of intermediate between the two. So what I plan to do is quickly show you a few examples and photographs of each of these designs. So this is a dual undershot water wheel design. And it's a very early design. You can see it's wooden, and you see the paddles around the circumference of each wheel. Now you can't actually see any water because it's below the grass level in this image. If I was more around to the right, you could see the water. But the water flows beneath the wheels, and the bottom of the wheels actually dip into the water. And as the water moves past the paddles at the bottom of the wheel, the wheels turn and rotate. And this design depends on a pretty good velocity of water past the wheels to actually rotate these heavy wheels and the equipment that's just on the other side of the wall there. But this was a simpler design than some of the other water wheel designs because it doesn't require a lot of construction to build tall dams and delivery systems and flumes and things like that. And this is another illustration of a common undershot water wheel design. And you see there in the right foreground, there is actually a very low dam that stores some water in a mill pond, so you have enough supply to be able to generate for some period of time, like a shift during the day, without running low on water. And then you see the stone mill race just to the right and in front of the wheel that actually delivers water under the wheel and rotates it. Now, this wheel design uses more of a blade technology as opposed to a paddle technology, which is a little more recent design. That previous design was medieval. This is more 1800s design and a little bit more durable in most situations. And one more, this illustration shows an undershot water wheel actually in operation. And this is the Robert Jemison Mill in Mountain Brook, Alabama. And millers thought for many years, actually for centuries, that their undershot water wheels were doing a good job because they usually turn very fast. In reality, once technology reached the point the efficiency could be measured, most undershot water wheels were not more than about 20% efficient. So they weren't in reality doing such a good job, but in a stream where there is rapid flow and continuous flow of water, they still did fine. Now, at the other end of the spectrum, we have the overshot water wheel. And this is a nice, simple photograph to show what an overshot water wheel looks like. You see that there's a wooden flume, and that's what we call the delivery system most often with a water wheel. There's a wooden flume that provides water to the top of the wheel, and there's a gate just out of view, kind of to the right where those bushes are, but before the spillway, where you admit water to the wheel. And as the water flows over the wheel, the weight of the water in the buckets on the wheel rotates the wheel. Because unlike an undershot water wheel, these are not so much paddles as they're actually blades that are closed on the wheel to hold the water, and those are called buckets, and gravity with the weight of the water pulls the wheel to rotate it. But you see what's required here. On the left, there's a very high dam that had to be built and has to be maintained to be able to deliver water to a height to go over the top of the water wheel. This is the Leffler Mill in Marietta, Georgia. And my experience I remember here is getting down this steep overgrown bank just behind me to get down where I'm standing to.
Dan, you went mute. Check your mute. Check your microphone.
Okay, I'll have to come out of.
Now you're back. Now you're back.
Okay. So do I need to just pick up where I left off? Okay. Apparently I was on mute for a minute, but I'm back now. And once I reached the water level, I had to find a place to stand to get the perspective that I wanted. And of course, I'm in the middle of the stream, so I'm balanced on rocks to take this picture. These three photographs show you a little bit about how the water delivery system from overshot water wheel works. In the top picture, which is me, yours truly, I'm actually opening a lift gate at the mill pond to admit water to the flume that will then pass over the water wheel. And I can control how much water I admit to control the rate of rotation of the water wheel. The lower left image, you can see the flume with the water flowing through it. And then at the right, you see the other end of the flume and the water wheel. And actually that photograph is about 25 years earlier than the picture at the top. They're both me. But you can see the buckets on the metal wheel that would retain water for about a third of the revolution and rotate the wheel and operate the machinery. Now, one of the questions I get quite often is why do water wheels look so different? In this picture on the left, you see it's a very low but wide water wheel. And then on the one on the right, it's a tall, thin water wheel. Well, it depends on the available water supply. If you have plenty of water, you can operate an overshot wheel with a relatively low but wide wheel. If the water supply, the volume of water is more limited, the millwrights typically would go to a taller wheel and a narrow wheel to be able to take best advantage of the limited but available water. This mill on the left is the Bunker Hill Flour Mill in West Virginia, and the mill on the right is the old mill at Mount Berry in Georgia. This is just another image of kind of a very interesting trestle structure for the flume at an overshot water wheel at Bale Grist Mill in California. And this is an overshot water wheel in Virginia at the Francis Mill. Now, one of the things I want to comment here, I mentioned the 20% efficiency with the undershot water wheel. This is actually a FITZ, F-I-T-Z, overshot water wheel. And this was a design that came along about the turn of the century in the early 20th century that could actually achieve an efficiency of almost 90% by delivering the water to the wheel about 10 inches before the actual top of the wheel and designing the maximum number of buckets and the right angle of the buckets to hold the water just as long as possible. Now, when you look at this delivery system at the end of the flume, which is actually a pipe for this mill, it almost looks like it releases the water too early. Well, there was a design that came along later I'm going to talk about in just a minute that talks about a design for the wheel where you in fact do that. And it's a follow-up to the comments I'm making now about the breast shot water wheel. So you can see here with this water wheel, the water is being delivered about 2/3 of the way up the wheel, and the wheel is going to turn in the opposite direction of an overshot water wheel. So it's sort of going to turn counterclockwise and backward. Well, there's enough water here to provide an adequate supply for milling operation without having to have a dam all the way to the top of this tall wheel. So that's called a breast shot wheel. And this is a really good example of a breast shot wheel in the Southeast. This is the old mill at Pigeon Forge, and the water's delivered just over halfway up this wheel, which this mill dates to about the 1830s. This particular picture is actually a black and white that I oil painted, and I took this picture in the mid 80s. So that's not even the same dam that's there anymore. And this picture was taken before that large restaurant was added to the right. One more picture of breast shot water wheel in rural Virginia. This is the Pine Creek Mill, and you see where the flume delivers water about 3/4 of the way up this wheel. Now, I mentioned the issue with delivering water a little before the crest of the water wheel. An additional technology that developed later in the water mill technology cycle was something called a pitchback wheel. And this design provided a flume that delivered water just before the top of the wheel, and the wheel turned backwards like a breast shot water wheel. It's called a pitchback wheel. Why would they want to do that? Well, with an overshot water wheel, the wheel is actually rotating in a direction that's opposite of the water flow in the stream. So in this photograph, if the water below the wheel is high enough that it's actually touching the bottom of the water wheel, then you have resistance from the flow of the stream versus the rotation of the wheel, because the wheel is turning clockwise and the water is flowing from left to right. So it's going to hold the wheel back. Well, if you use a pitchback wheel, you get almost as much gravity advantage as with the overshot wheel, but you now have the wheel rotating in the same direction as the stream flow. So you can achieve a 90% efficiency with the pitchback wheel. These receive limited application in part because other technologies came along and replaced the water wheel, but it's really a clever design. And this is the Bagnell Mill on Prince Edward Island. I have not actually seen many pitchback wheels. A couple more comments on water wheels. This is a water wheel that's actually inside and below the mill. And why would they do that? Well, in cold regions where the water freezes up a lot, there's a lot of snowfall, they may have months when they can't operate a water mill because the wheel is frozen up. So there are a number of examples where the water wheel is actually moved inside and under the mill. Of course, they have mildew and rot and other problems associated with that, but at least they could operate all year. Now, this is an undershot wheel, and it would turn counterclockwise, but this is a stream where it's actually operating, so they have plenty of water, and a 20% efficiency is not a problem. This is Slater Mill at Pawtucket in Rhode Island. Just another illustration of dual water wheels. These are dual overshot water wheels. Each operates its own set of milling machinery inside the Aldi Mill in Virginia. Now, this is the very most primitive design for a water wheel. It's a pioneer, like a frontier horizontal water wheel, which is a little more than just a wagon wheel that's been adapted with blades to rotate. And you see the flume or the delivery system, and it just kind of spins the wheel. Very low efficiency, but very easy to set up and operate. That vertical shaft, which looks like about equivalent of a 4x4, although I'm sure it's hand hewn, goes directly up to the millstones that are just above that floor at the top of the picture. Now, interestingly, that very primitive technology actually evolved into something called the water turbine that's still used in hydroelectric facilities to this day. And this is a picture of a water turbine at a water mill that's actually where you can see it. A lot of them are underground, or they're under the mill where you can't see them. But this one is suspended above the stream, and you can see the water zipping by just below me. But water enters this thing, spins the blade, and then spins that vertical shaft going up into the mill. This technology really kind of came on its own in France in about the 1840s, and it became widespread in the United States during the late 1800s because they were more powerful and generally less maintenance required than with a vertical water wheel. Just a few examples of what some old ones look like without the housing around them, so you can kind of see the blades. These are pretty common at milling sites and historical exhibits and places like that. One more comment on water wheels and water mills. There's another technology that was somewhat popular in coastal areas, especially in Britain and New England and the Atlantic provinces of Canada, and this was a tidal mill. Now, this mill pond is actually a tidal basin. And you see there's a dam, which they call a causeway, just below the mill and exits off to the right. That holds the water in this mill pond. So at high tide, the miller opens the gates and lets water flow into this mill pond. When the tide turns and starts going out, he closes the gate and traps that water in his mill pond. And then as the water recedes at low tide, he's able to generate with the water from the mill pond under the mill. So on the left, you see the water level at low tide. On the right, you see the water that was trapped at high tide in the mill pond. And he opens his gates under the mill, and I'll show you the wheels here. There are 2 water wheels under that mill, and he releases that high tide water at low tide, and he's able to generate until the tide starts coming back up and he can refill his mill pond. These are some very ancient water wheels, but it's the best photos I could get. I suspect this one on the left is probably at least 500 years old, but the one on the right is also very ancient also. So we talked about water wheels. So how does a grist mill operate with a water wheel? You see the flume and the water wheel on the right, and then you see a drive shaft that is connected through the center of the water wheel. And then you see something called a pit wheel and a lantern gear. So the wall of the mill building would actually be between the overshot water wheel and the pit wheel. Now with a vertical water wheel, just think about it for a minute, you have a horizontal drive shaft. So the drive shaft is rotating horizontally, but the millstones need to rotate horizontally also. So you need to change the direction of the drive shaft rotation by 90 degrees to be able to rotate your horizontal millstones. That's what this is illustrating. And traditionally, that was done with something called a lantern gear or a bird cage gear. And you see that just adjacent to the pit wheel. And then that vertical drive shaft goes up to the floor above where the millstones are located. And there are 2 millstones. There's a base stone, which remains stationary, but it has a hole through the middle. Above that, there's an upper millstone they call a runner stone because it turns. It turns over the stationary base stone, and you grind the grain between the 2 of those. And it's all enclosed, generally in a wooden housing that millers call a vat. And above that, you have a hopper where the grain is fed into the millstones and some sort of mechanism that controls the rate of feed. In the older mills, it's wooden and called a shoe. And I'm going to show you a few pictures of these now. So this is what a lantern gear and a pit wheel actually look like. Now, just behind that wall, behind the pit wheel would be the water wheel on the outside. So the pit wheel turns in time with the water wheel, and then it connects with this lantern gear to actually change the direction of rotation to vertical. And you can see a little bit of the vertical drive shaft at the top. Now, by designing the right number of sprockets on this lantern gear, you can control the rate of rotation of the millstones in the mill. So generally, the water wheel is going to be turning at about 10 or 12 revolutions per minute if it's operating well. The millstones need to run at about 120 revolutions per minute to do a good and efficient job of grinding the grain. So you calculate the number of sprockets you're going to need to be able to step that speed up from about 10 or 12 to about 100 or 120 from the water wheel to the millstones. Now this shows a more complicated design for gearing inside the mill. This is all wooden gearing. The water wheel is on the outside wall, just past that wall to the right. You see the big pit wheel. And in this photograph, you can see the massive drive shaft. And because of all the torque and energy produced by that water wheel, these things quite often were massive. They might be 25 or 30 inches in diameter from the very finest hardwoods the millwrights could come up with when they're building the mill. So this mill not only operates a lantern gear, but it is designed to operate all kinds of equipment through the mill. So this is what is called an automatic mill, because it's actually moving the grain and the flour and the cornmeal around through various automated steps without the miller having to do everything manually. It's all wooden. Now, by the late 1800s, metal began to replace a lot of those wooden parts. So here you can see the pit wheel to the right, and you can see various metal bevel gears that are being used to make that transfer from horizontal to vertical to operate the millstones. And then there were some mills that were belt and pulley driven. And this is an example of that. You see the big belt and pulley and the water wheel and flume in the background, and that belt is transmitting the energy into the mill. So it's a little more flexible design, probably a little easier to design actually, because it's a little more forgiving with the belts that are involved. Now here we are actually in the grist mill, and this is yours truly again at Tannehill, and I'm standing beside the millstones. And the millstones are enclosed in that wooden vat with the orange stripe at the bottom, and they're actually rotating. And you see the hopper that delivers the grain to the stones. And at the top, there's kind of a little reddish piece of wood my hand is on. That's actually a screen that helps filter out any corn shucks or debris or anything like that that's in the corn before you grind it. And my right hand is on the mechanism that controls the rate of release of the corn kernels into the wheels below. Now, a lot of mills have two sets of stones. They'll have one set of stones to grind corn, and then they'll have another set of stones to grind everything else, because corn kernels are so much larger than wheat or any other kind of grain. The spacing and tolerance between the wheels is very different. So rather than reset that all the time, a lot of mills have two sets of stones, and that's what you see here. And then you see the bins where the ground flour and cornmeal are collected and then placed into bags for sale or use or returned to the farmer that brought the grain or whatever. This is Mingus Mill in Cherokee, North Carolina. This lets you see what the corn looks like in the hopper, and you can see a little better the mechanism below there, and you can see some of the top of the vat that's leading down to the millstones. You can actually see a little bit of the runner top stone kind of inside there. It's a little warmer colored. And this shows you the runner stone with the hole in the middle where the grain goes in to get between the two wheels to be ground. And that's a wooden shoe mechanism that controls the rate of release from the hopper just above it. These are a couple of millstone surface patterns. There are all kinds of designs that were cut into the surface of the stones to help with the grinding, to help the ground product move from the center of the wheel to the outside where it's discharged and collected, and to help keep the mill and flour cooler as it's being ground. So these are two of the more popular kind of patterns. And you can see some actual photographs here. Now, this picture on the left is a very telling and descriptive photograph. In the back, you see the wooden vat and housing with the hopper that's been taken off the millstones. And in the foreground, you see the base stone, which is stationary. It just sits there during operation. And you can see the furrows that are cut into it. That's the quarter pattern. And you see the spindle in the middle that connects down to the drive shaft and out to the water wheel, and that turns when the grain is being ground. And in the middle, you see the runner stone. It's larger and heavier than the base stone, and it's actually been lifted off and set aside so they can resurface these stones. And they do that regularly when they're operating. Now, there are all kinds of controversies about how important is that, the different patterns and so forth, but it's a ritual that's been gone through for centuries and it's still used. And in the right photograph, you can see a couple of different patterns which are the same patterns that were in the illustration I showed you earlier, the sickle cut and the quarter cut. Now, technologies evolve, and so did technologies for grinding grain. The technology that has essentially replaced millstones is the roller mill. These are early roller mills on the left. They use metal wheels to grind instead of millstones. Again, as technologies evolve, it's controversial. And some people didn't like it. There's still people that only use stone ground meal. But most of what we eat and the bread we buy, of course, is ground now on metal rollers. And it's efficient. And I think a lot of the nutrition experts actually think it does at least as well or a better job. And it is a lot faster. So these are examples of early roller mills. So there are no millstones in this mill, just metal rollers. On the right is an example of vertical millstone. So this is a vertical mill, and the grain is ground on the edges of the stones. Other than that, it's very much like the traditional millstone illustrations I've been showing you. So moving along, the other common application, particularly in the eastern United States, was the sawmill. And actually, when the first settlers came to the New World, they established more sawmills than they did grist mills because the European mother countries wanted the lumber for shipbuilding and for construction and so forth. So when the ships came over from Europe, they brought flour for the settlers, and then they took the lumber back to Europe. So this is the early design for a sawmill. It's called a sash saw. It has a frame that's very much like what we think of as a window frame that goes up and down. It's a vertical saw, like a two-man saw that saws the lumber, and it operates off a crank. And you can see that illustrated here as the crank raises and lowers that two-man type design saw. And of course, in Britain, the sawyers, S-A-W-Y-E-R, there was a union for them, and they didn't like this technology because they thought it was going to replace their manual two-man sawing operation, and of course it did. It's much faster and more efficient. This is a photograph of a sash up and down two-man type saw. You can see the blade kind of in the background. It's a little rusty looking, and a piece of wood here being cut. And this frame is designed so that as the saw works, the water wheel inches the wood into the saw blade until it's all cut. So it's really a pretty clever design. But that sash saw was soon replaced with circular saw blades, which did an even better job. And that's what you see here on the left. On the right is actually a water-powered bandsaw that dates to about 1840 that I happened to see in a mill up in New England. Another application for the water wheel is the iron furnace. The water wheel you see here in the foreground, this is the Ropes Valley water wheel at Tannehill Historic Park in Tuscaloosa County, Alabama. And it rotates to operate bellows. So what you see in the photograph on the left are bellows. And the mill mechanism is the same as for the sash saw. It's like a window frame, and it pumps this bellows open and close to force air into the furnace and produce a higher quality iron product. On the right is a water-powered ore crusher that has hammers that the mill raises and drops to crush ore that's going to be processed in a foundry. This is a black powder mill. So this is part of the DuPont mill in Wilmington, Delaware. And you see it's stone. It's like a bunker for explosions. We talked about that earlier in part one of this presentation. And what you see here is actually a canal that delivers water to at least about 12, maybe 20 mills at this DuPont operation up and down the river. The river is just behind the mill. Water's diverted through this canal and released in turn to each of the mills that are located along the canal. And this is view inside. So water power and a water wheel are used to grind and prepare the different components of the black powder, and then to mix those into the products that were used, like in the War of 1812 and Civil War, and up until about the early 20th century, I think. And adjacent to that mill, because this is a historical railroad group I'm speaking with today, this is a steam engine that replaced the water wheel at that mill we just saw a little bit earlier. And you can see on the left what looks very much like a locomotive, but it's actually providing power to a mill instead of turning the drivers on a locomotive. The ultimate application of the water mill and the water wheel was the textile mill. These were massive mills, particularly in New England, and in England, they literally drove the economy. They changed the way of life. People moved from rural areas to urban areas to work in these mills. And there were social issues associated with that. Child labor is one, the number of hours people were required to work, safety issues associated with being around these powerful machines. But nonetheless, they were there to make wool and cotton cloth. What you see at the top are water-powered looms. Just below that are water-powered spindles. And the two photos on the right are carding machines. And we can't get into a lot of that today. That would be a presentation in itself, how all this worked. But these water wheels were massive. They operated machinery on 3, 4, 5 floors, and just a tremendous amount of power. And belts were generally used to deliver water to each of these pieces of machinery. And there was a handle that engaged the pulley in the belt for that piece of equipment to operate it. And they just ran throughout the mill. And this shows you a little bit about what some of those belt and pulley systems kind of look like that were usually overhead where all this equipment was running. And these are water-powered machine shops that operate on the same principle with belts and pulleys overhead. So you're able to engage your drill or your saw or your lathe by pulling a lever that tightened the belt that operated that piece of equipment. And this is kind of a unique application for water power, but this is the Pratt Cotton Gin Mill in Prattville, Alabama, which many folks who are watching this today may have seen. If you haven't, you need to make a trip to Prattville and experience this. This is a massive water power plant, as large as any textile plant, and it dates to 1840, and they use water power to make cotton gins. And you can kind of see where the different sections of the mill were added over the years. But it's quite something to see. There's really very little, if anything, inside it anymore, and the plans are to convert these to historic condominiums. And their issues are being worked with now over, how that's going to move forward. And then we have mining operations that were water powered. Water wheels were used to pump water from underground mines. That was one of the first applications for a water wheel, were to use bucket lifts and other technologies to get water from underground mines. In fact, I read that recently archaeologists have discovered 150 feet underground in Wales a Roman water wheel, or the remains of a water wheel, that they were using to pump water from a gold mine there. But water wheels were used at mines to pump water out. They were used to crush ore, and they were used to deliver ore great distances, even over mountains, in bucket lifts and things like that, to get them to the actual mill and mining operation that company might have. This is Champion Mill and Mines in Colorado. And now I want to make a few comments specifically as I wrap up about Komolga Grist Mill. Komolga Grist Mill is located in Childersburg, Alabama. It was built in the early 1860s as a commercial scale mill. This was not a country mill. This mill could process 1 million bushels of corn in a year. It was and still is a large mill. And James and I are proposing that the Mid-South chapter plan a field trip here. And we have been invited. So it's just a matter of scheduling the date and the time. I was fortunate enough to get to do a feature article for Alabama Heritage Magazine in this past winter's issue on Komolga Grist Mill. You can still buy back copies of this from the Alabama Heritage website, or you can check the Childersburg Historical Commission website. And from what I understand, they have the article there now, or they will very soon. But it tells you all about the mill and how it operated. But this was a mill where the flour and the corn were delivered by rail. And Norfolk Southern still operates one of the oldest, some people say the oldest rail line in Alabama, just a few feet, not more than 50 feet from the front of the mill. And back in the day, there was a siding here where the cars were unloaded into a bunker under the mill. And that bunker was below that midsection you see there, just to the right of that big grain hopper and to the left of the actual dark wood structure, there's a tin roof. Well, that's where the cars backed up to that, and they unloaded their grain underneath the mill right there. But Norfolk Southern still runs typically each way one time during the day. I've been there a number of times when the train comes through. In fact, in the summertime, they have a Tuesday evening fish fry. And from what I've been told, the train drivers, engineers, will plan their return trip in the evening so they can stop the train, they can enjoy the catfish fry, and they let the kids who are there see the trains and tell them. I think they may even let them inside the locomotives. I'm not sure what they're allowed to do or what they're getting away with. But I haven't been there for that, but I hope I get a chance to do that this year as the COVID maybe gets under control a little bit better. This mill was always turbine operated. It never had a wheel. It operated on 3 big water turbines. This is pictures of 2 of these. And this is a mill where to some extent you can see under it. I happened to be there when the water level was very low, and I went under to take this photograph. But the energy from those turbines is transferred through a series of mostly metal, but some wooden gears up to the milling equipment above, which is just above that sort of white and orange area at the top of that drive shaft. And by now, you've seen what grist mill vats look like. These are 2 vats. The one on the left is for corn. The one on the right is for wheat. This mill actually had 5 of these back in the day. The Millstones came from France, and it was quite an operation. And because this is a commercial mill, it's ideal for a field trip like our group, because this mill is spacious inside. They conduct tours here all the time. Children's groups and scouting groups and things like that come here. Church groups come regularly. And there's plenty of room for people to walk through and see what goes on and understand a little bit more about how milling worked. This is one of the original French millstones that was brought over during the Civil War, and you can see that. It's a design where I didn't talk much about what millstones are made from, but they're sorted materials from sandstones to granites to quartz and all kinds of different materials that that are available in different places and different mills were able to acquire. This is assembled in sections and then bound with a metal band to hold it all together. And they also do have a vertical mill there. I mentioned that a minute ago with vertical stones. And this is actually what they're using now for their demonstrations. And right now it's electrically operated till they can get at least one of those turbines back online. So when children come, what they're allowed to do is to grind corn. Then there's a building adjacent to the mill where they actually make their own cornbread and get to butter it and eat it while they're there. So that's just got to be a great experience for the kids. This was an automatic mill. When the grain arrived at the mill, it was unloaded from the rail cars and the miller literally did not see it again until it was ready to be put into bags and barrels at the end of the process. So this is a bucket lift that would carry that grain to the upper levels of the mill. This is an auger that took the ground product to be separated out, to different qualities of flour and mill. And this is actually an upper level in the mill that we can see. You see all these incredibly complex belt and pulley arrangements that are there. The miller can explain some of that to us. On the left is a wheat cleaner. On the right is a corn cleaner to be sure the product is clean before it was ground. This is a better view of the corn cleaner. You see the various belts and pulleys there. And this is Mr. Ron Smith, who is the miller. If we go, we'll arrange so he can host us a tour. He has his hand on the wheat cleaner. And I want to call your attention to that big pulley just above his head. This is a close-up of that pulley. This pulley was built by an enslaved artisan in the 1860s, and it still works. It is just absolutely beautifully designed, and the way it's laminated and put together, the way that amazing what these people could do. This equipment is literally like furniture quality. It's mostly built from heart pine, but it almost looks like it's cherry or mahogany. What you see here is what's called a bolting machine. It's like a sieve. It separated flours into fine flour and middlings and brand, I think into about 5 different kinds of products. And there are 3 of them here. The lower one is actually open where you can see part of the silk screen. Just above it is the second one, and behind it is a third one. Because they produce so much flour, they had to have 3 of these machines running to be able to process it all. And this is the packer where the final product comes out and is loaded into barrels and sacks to be carried away in wagons or, whatever sales mechanism, probably some of it left by rail also. And when the very first cornmeal came out in the 1860s, the miller nailed a bag of it to the wall and wrote this just below it, first corn mill. And he spelled mill, M-I-L-L. But that you can still see that on the wall there. So that's what I have to share with you today. I hope you get an opportunity to pick up a copy of my book. I'm still busy with my previous books, especially Historic North American Locomotives. This book is still selling quite well, and it's available. My first book, The Art of the Locomotive, is a little harder to find now. There still are some new copies. You can't get it from Amazon anymore new. You can buy used copies though, and they have some secondary sellers, I think, that have new copies. What am I working on now? Right now, I'm busy with my upcoming project on historic fire trucks. In fact, I've been working on that this week, and it's moving along quite well. I'm continuing to work on another watermill book called Watermills of the Old South. These are old mills that didn't make the cut for the University of Alabama book, many of which are not even there anymore. These are photographs I took years ago, and none of the mills you see here exist anymore. But I think it would be important to preserve that part of our history, including one nearby here in Helena. This dam is still there in Old Helena, but this mill is long gone now. This is a photograph I took many years ago, and this was actually an early electric generating station. So I hope you have a better appreciation now for watermills, how important they were, and what they did for us. And it's very important that we be aware of preserving our history. And this is our family from the left. This is Grant, Kathy, Kevin by the water wheel, Dory, and yours truly on the right. So I appreciate your attention, and I hope you enjoy this presentation. If you have any questions or any comments, I would love to hear from you. Thank you very much.
Thank you very much, Ken. And I will just ask a couple of questions.
Sure.
I don't think you covered this. One of them is about how long did the stones last before they had to pull them up and regroove them?
Well, in some cases, if they were grinding a lot, and depending on what they were grinding and the material in the stones, it was literally done every several weeks.
Wow.
In other cases, say Komolga, for example, I think they grind those stones about once a year. And there's a fellow in Tennessee at Falls Mill, and he comes down and grinds the stones for them. And I mean, not grind the stones, resurfaces the stones. And one of the common expressions now is showing your metal. And that is a milling terminology because they use metal picks and tools to resurface the stones. And if you were good at it and you had been doing it for a while, you would have metal filings in your skin and you could show your metal. So,
So another question that was asked on the previous part one presentation was about the wooden gears
yeah.
and how long they last and how they had to replace those in the metal versus the metal gears.
Right. And that was an ongoing process. They used the best woods they could come up with wherever the mill was located. They looked at the hardness of the wood and its durability and also its potential for rot. And those weren't always the same. You might have one kind of wood that was very hard and would last a long time as far as the milling is concerned, but it was more prone to rot. So depending on what part in the process, from the wheel to the gears, to the cogs and sprockets on the gears, they would use maybe a number of different woods. But then once the metals came along, the metals began to replace wood over a period of a number of decades. And there were hybrids too, and you still see hybrids in mills where part of the drivetrain is made from wooden components and other parts are made from metal. And I think one of the most interesting examples of that we would see at Komolga, and that's where the actual structure of a gear is metal and the shaft is metal, but then the actual sprockets or cogs on the gear are made of wood, because the wood was easier to repair and replace than a metal gear. You could just literally take a mallet and hammer a damaged wooden sprocket out and hammer another one in, and you were back in the milling operation. If you broke a metal gear or a sprocket on the gear, you had to take the mill offline. Usually you had to take that gear out, which was massive, take it to a blacksmith shop and let him repair it and reinstall it. So you might be down for some extended period of time in that case. So there were various advantages to each material. Another important design consideration to make these things last as long as they could was to be sure you had an odd number of sprockets or cogs on your gear, so the same surfaces are not continually making contact over and over. They're mating up with different wooden surfaces with each revolution for a while, and that could significantly extend the life of the equipment too. Does that answer some of that question? I think you're muted, James.
It's really an artisan kind of operation. I mean, there were artists
It is.
in a way that had to figure all that out and create it and spread the technology around. Well, one of the things I have read in the past, and I'm not sure exactly where, but that in the Birmingham area, Weddell, Weddell, was the original location we now know of as Mountain Brook, and that there was a mill there that was more of like a commercial mill, and it ground the grain for the farmers who live south of Red Mountain, because the farmers there could not get up and over the mountain in those days. And so there was a mill operation there in Waddell that ground the grain for them because they couldn't take it up and over the Red Mountain into the valley that we now know of as Birmingham now.
Yeah, that's interesting. The site we now know as the Robert Jemison Mill, or the old mill at Mountain Brook, is not an actual grist mill.
Right.
That mill was built, though, on the site of a real mill. The old Perryman Mill was there. So it is a good location for a mill. But that beautiful Robert Jemison Mill was built as a promotion as Jemison was trying to develop that area residentially. But it's interesting you mentioned the farmers coming to the mill. because the farmers from some radius, depending on, what travel conditions were like, how large the mill was, what other mills were available, they would travel to the mill to have their grain ground. Well, during peak harvest season, they might have to wait for several days for their turn at the millstones. So they had to have things to do. And in a lot of cases, that was their big trip of the year. They might take the children. If the wife was lucky, she would get to go. Quite often, she didn't get to go. But they would sit around and they would tell stories and they would fish and trade and, all kinds of things would go on while they were waiting. And as a result, a lot of these mills became the hub for a little community. A store might spring up there, a little hotel. Next thing you know, there's a church there and maybe a school there, and you have a little town that's developed around the mill. And in some cases, the railroads, would design their route to go by that little community. Because they could trade there, they could pick up and they could sell and so forth. So they were really fundamental to early social life, particularly out in rural areas.
When we do a outing or a picnic for the chapter at Childersburg, one of the things that people can do earlier in the day is go by the marble quarry in Sylacauga, and there's an overlook there that's open to the public, and people can see that very ancient, that continues to this day, marble quarrying operation that's a big deal and has been in Sylacauga for all these years. So both of them right down there together. Make a day trip out of it.